one thing I'd like to start by doing is to demystify a bit more this whole business of the neighbor joining correction with its sort of mysterious correction factors. Last time I tried to convince you that the special form of this, and specifically this 1 over n minus 2 factor, has a special property, namely that it makes external edge lengths not matter at all for the function qxy that we minimize. Basically, a given external edge length will contribute to all possible qxy. In other words, that function q for all possible pairs xy, that external edge length will contribute an equal amount to every single one of those. So clearly it can't drive the choice of which one will be minimal. I'd like to follow up on that same kind of logic to actually prove that the minimal qxy will actually pick a neighbor, which is clearly requires a bit more than simply showing that it's insensitive to external edge lengths. But actually the analysis is really simple, and it follows more or less the same kind of logic of basically counting how much each edge length will contribute to these different possible q for different pairs, different sequence pairs. So the strategy that we're going to follow is basically to assume that we know a specific pair A, B actually are neighbors, and then to consider the contributions of different possible internal edges to QAB, and also for any other sequence C not equal to QA or B, the contribution of those edges to QAC. Okay? So basically we're saying take one of the sequences that has a known neighbor B, and now consider its Q versus any other sequence C, in other words QAC, and now we're going to consider how different kinds of internal edges contribute to QAB versus QAC. Okay, so the basic aspect of this that matters is what kind of edges do we actually want to consider. Well, the good news is that we've already considered external edges, right? We've already shown that external edges contribute equally to all possible qxy for any possible pair xy. So we can restrict our attention exclusively to internal edges. It may help to just make a few little drawings here. Oops, what's going on? Okay. So let's focus on a particular edge, and now let's imagine the different possible scenarios that we need to consider. So let's suppose, for the purpose of argument, as I said, that A and B are actually neighbors, in other words, connected by one node on the path between A and B. And then we can imagine that there's some number of edges that connect that node to the node that's at one end of the edge that's of interest to us here. So then we're interested in any other possible sequence C, what are the possible cases? Well, I'm going to argue that there's really only two cases that we need to consider in which logically capture the entire set of all possibilities. Namely, that either C is on the same side of this edge as A and B, so that would be the case where with some number of interconnecting edges we finally get C over here, or conceivably over on this side as well. It could be connected over here somewhere. Okay, so that's one scenario. And the other scenario is that it's connected somewhere over there. Okay? So the two possible cases are different in the following sense. In one case, this edge that I'm zeroing in on is on the path between A and C. Whereas if it's on the same side of that edge as A, then this edge is not on the path from A to C. And I think you can see just logically that I've just split the set of all possible internal edges into two disjoint subsets, right? The set of paths, edges that are on the path from A to C versus the set of edges that are not on the path from A to C. Okay? So I'm going to now confine my analysis to just those two cases. So here's the setup, same as I just said a moment ago. A and B are neighbors, and now we're considering A versus some other sequence C. So here are my two possible cases. I've got an edge of length gamma that is on the path from A to C. And for simplicity, I'm going to keep a count of the number of sequences that are on this side of the edge. So basically I'm saying lowercase n is the number of sequences that are on this side of edge gamma. Then here's another possible edge that is not on the path from A to C. In other words, A and C are on the same side of this edge. And again, for convenience, I'm going to just have a number that specifies the number of sequences that are on this side of this edge, which I'm going to call delta. In other words, this edge, its edge length is delta. So I'm also, just for completeness, going to annotate the total number of sequences on this side of the edge must be the total number of sequences, capital N, minus the number of sequences that are on this side of the edge, in other words, lowercase n. So in addition to sequences A and B, I also have n minus little n minus 2 other sequences on this side of the edge. Any questions about the setup so far? Is all that clear? Question?
The minus 2 and the minus 1, how does it count for A, B, and C?
Exactly. Right. So I have one sequence there, and I've got n minus 1 other sequences for a total of little n sequences on this side of the edge, and A and B plus n minus little n minus 2 other sequences on this side of the edge. Okay, so same basic setup for my other edge delta. Little m sequences on this side of the edge, and A, B, C plus n minus little m minus 3 additional other sequences on this side of the edge. So now, with that in hand, question?
What's big N, little n?
Big N is the total number of sequences in the whole tree, including A, B, and C. And little n I just defined as the number of sequences that are on this side of edge gamma, in other words, the side opposite to sequence A. And then little m I defined as the number of sequences that are on this side of edge delta, in other words, the opposite side from A. Okay, so on this basis, I can now go ahead and calculate these two edges' contribution to QAB and QAC. And I'll just make a note that, of course, there are lots of other edges that contribute to QAB and QAC. Every single internal edge in the tree contributes to every Q for every possible pair, right? But all those cases will be exactly like these two cases, because these two cases cover all the possible contingencies. Either those edges are on the path from A to C, or they're not on the path from A to C. So there will be a bunch of other terms that will be just exactly like these terms, except the little n and little m will be some other number, okay? All right, so let's consider QAB. So remember, the first part of QAB is just actually the distance from A to B. And I want to emphasize that since A and B are neighbors, no internal edge can possibly contribute to that distance from A to B. Why? Because A and B are neighbors. There are no internal edges on the path between two neighbors, right? Neighbors are defined as a pair of sequences that are connected by a single internal node with no internal edges from internal node to internal node, right? Is that fine? Okay, so I'm going to make that explicit by writing a 0 here, that neither of these edges, gamma or delta, contribute anything to the actual distance from A to B. So all that's left now are these so-called U terms that are 1 over n minus 2 times a sum over basically distances from A to all other possible sequences and distances from B to all other possible sequences. And we can immediately write down what the contributions for edge gamma and edge delta are going to be for that. So, so for the U going from A, I've got A going across edge gamma to little n other sequences. So I'm going to have an n gamma coming from UA, right? Is that fine? Any questions about that? And I'm going to have exactly the same thing coming from UB, because A and B are both on this side of this edge that goes to little n other sequences with edge weight of gamma. So I get a 2n gamma for the gamma edge, and it's exactly the same thing, but with little m instead of little n across edge delta. So it's 2m delta, okay? Now we need to consider the case for A to C. So the crucial thing is that since gamma is on the path from A to C, it does contribute to the distance from A to C. Counts exactly once. It contributes gamma to that distance from A to C, because it's on the path from A to C. So I write down a gamma here instead of a 0. Delta is not on the path from A to C, so it doesn't contribute here to the distance from A to C. Okay, now I have to consider my U terms for U of A and U of C. Well, the situation for A is more or less the same as it was before. I'm going across edge gamma, just little n times. So there's my little n times gamma. And then for C, I'm going across edge gamma in the other direction to basically capital N minus little n sequences. right? Because that's how many sequences are on this side of edge gamma. So that's plus n minus little n. The little n's cancel. I just get capital N, right? Then for my delta, A and C are on the same side of delta as A and B were, so we get exactly the same thing, 2m delta. Okay. My gamma terms, I want to collect them. I think you'll agree I have n minus 2 over n minus 2 gamma coming from here. I'm just going to add that in here, and the total result that I'm going to get is keeping the 1 over n minus 2, or minus 1 over n minus 2 factor out here in front, same as I had over here. It just reduces to 2 gamma, okay? 2 gamma plus 2m delta. So the first thing I want to point out is that for any edge delta that is not on the path from A to C, again, just like the external edges, it contributes the exact same amount to QAB and QAC, okay? So basically, it doesn't matter in our selection of which Q. And actually, this is a more general case of the external edge argument that we made before. What's an external edge? An external edge is an edge with an m value of 1. So we actually got our earlier result over again here. 2 times 1 delta, basically, it's the same result we had before. Okay? External edges, they always contribute the same amount to every Q. So they don't matter for choosing which pair minimizes Q. Okay, now let's look at the case of an edge that is on the path from A to C. Well, for any internal edge, it must have at least 2 sequences on each side of it. It's an internal edge. Internal edges, by definition, always have 2 sequences coming off on each side. So n is always greater than 1. Therefore, 2n gamma is always greater than 2 gamma. Therefore, QAB is always less than QAC for any C that is not the neighbor of A. So we basically just proved that the global minimum of Q for over all possible pairs must be neighbors. Because if it's only the neighbors that have this 0 in the positive term, the distance from A to B. Any other non-neighbor is going to have a positive contribution here, which causes it to be not the minimum. That's the special characteristic of this whole function, is that only neighbors will not have internal edges showing up here in the distance from A to B, because they're neighbors, therefore there is no internal edge on that path. Questions about this?
Can you draw the difference between an external and internal edge?
So an external edge leads directly to a leaf node. So, if we just draw some tree structure, then clearly all the termini we can label as leaf nodes. And then the external edges are the ones that link to a leaf node. So then the remaining edges are the internal edges.
So there are 4 internal edges.
1, 2, 3, 4, 5, 6. Did I miss any? 6. Other questions? Okay, so I want to zero in a bit on the interpretation of these unrooted tree structures, since I think that's an important kind of conceptual understanding of what they really mean. Question?
Is N gamma and the lower capital depends on which gamma. It depends on
Which edge?
it is.
Right. Each edge will have different numbers of sequences.
Yeah, so it is actually not all A times
Right.
N gamma and it is N gamma and there is a
Right. So each edge will have a different weight, if you will, that is characteristic of the number of sequences that are on that side of it, if you will, relative to, in this case, A.
Are gamma and delta some specific numbers? Or?
Is the edge length. Remember, in this whole additive distance tree, the total distance from a pair of leaf nodes is just the sum of the edge lengths on that path. So here I've taken the liberty of using the same letter, basically, for specifying my edge and the variable that is its edge length.